Welcome to this lecture on K-maps. Now remember before I taught you about product of sums and sum of products that allows you, which are two ways that you can take a truth table and generate an equivalent Boolean algebra expression so that the output of the Boolean algebra expression matches the output of the truth table. Well, in that lecture, I also said it was really important to minimize the number of gates that we use because AND gates, OR gates, and NOT gates all take up space on our chip and they use transistors. And the more transistors you use, the bigger chip you have to make. Also, the slower it becomes. Each gate makes the circuit run a little bit slower, so your CPU will run a little bit slower if we have more gates. They'll also use more electricity. So by minimizing the number of gates that we use, we are able to make smaller chips. They're cheaper to make, and they use less electricity, and they're faster. So it's really important to minimize the use of gates. So K-maps is one of several ways that you can create a minimal expression or an expression, Boolean algebra expression, that correctly gets the right output but uses the fewest number of operations or gates. So this right here is a 3-input K-map. Now you can have K-maps that uh, work with 2, 3, or 4 inputs pretty easily. And they even have some like 3-dimensional input K-maps where you can have more than 4 inputs, but we're not going to talk about those in this lecture. So the information in this truth table, we're going to represent all inside of this K-map. If you notice the output name, which I'm calling F, we just put up here. Now with 3-input K-maps, we take 2 inputs and we list them across the top. Now there is a version where you can put the 2 inputs down the side and kind of rotate this 90 degrees, but I'll just show you this one. So we take 2 inputs and we put them up here, and finally the third input goes on the up and down. The numbers across here, the zeros and ones, the first one refers to the first input A, and the second one will refer to B. So this is A and this is B. And same here, this one means A and this one means B, A and B, and the same, that one's A and B. Now these refer to C. And if you notice, we have every combination of A's and B's. And now we just need to take our output and put it into the correct squares, the squares that are labeled. So if you notice, this first row has all zeros. A is 0, B is 0, and C is 0. Well, here A is 0, B is 0, and C is 0. So we take our output, 0, and we put it inside of there. Now, if you look right here, the next one, A is 0 and B is 0, but C is a high voltage, so we use the C that's a high voltage. And we put our output there. Now, this next column, if you notice, A and C are low and B is high. So A is low, C is low, but B is a high voltage. So we'll take the 1 and put it there. So notice we have the 1, and that's why we put the 1 in there. Now the next one, C is going to be high, A low, B high, and C high. And that's this row right here. So we take the 1 and we put it there. Now you might notice, wait, 2's next, not 3. If you notice, I've swapped the 2 and 3 because if you're counting in binary, we've got 0, 1, 3, 2. So I'll tell you why I swapped it, but that is very important that you swap this. If you do not swap it, the K-maps will not work. So when I show you how and why these K-maps work, you'll see why these two columns are swapped. So the next two numbers are these two numbers right here, and I will put them here. Okay. And we'll just check. A is high, B is low, C is low. So 100, right? A is high, B low, C low. And 101, A high, B low, C high. Yeah. Now the last two will go numbers. These two will go up here. This is where all of them are high, and A and B are high, and C is high. So that's that one. So we put 0 there. And this one right here, we have A is high, B is high, C is low. So A is high, B is high, C is low. And that's a 1. Okay, so we've now filled in all of these numbers. So the way that it works, now there's going to be rules, and I'm going to give you the rules in a little bit. But basically what we want to do is we want to circle all of the ones and none of the zeros. When we make circles, we're saying those are our high values, or the voltages that should be turned on in these conditions. But there's a couple rules with the circles. They have to be in groups of either 1, 2, or 4, or 6. And you cannot circle diagonally. You can just circle horizontally or vertically. And I did say a group of 6. That's incorrect. You can only make circles the size of 2, 4, 8, and maybe 16. And if you notice, these are powers of 2. So the number of ones that you put inside of your circle can either be 2, 4, 8, or 16. Now, in this 2-input K-map, the biggest circle you can make is 8. You obviously can't circle anything more. There's only 8 squares in there. But when we have a 4-input K-map and everything is high, then you could circle all of them. So let's go ahead and start circling, and I'll circle in a color here. So we'll circle this one right there. And let's circle these two together. Now we might be tempted to circle this one by itself, and you have to circle all of the ones. You can't leave ones uncircled, and you cannot circle any of the zeros, so we can't make a circle like that. But it's okay to circle some ones more than once. And so the last circling we'll do will be this one right here. Okay. Now, let me just quickly review some of the other rules when we circle. Now, the first two rules that you cannot break, and I kind of already mentioned them, you have to circle all of the ones and no zeros. Also, the circle can or must contain 1, 2, 4, 8, or 16 ones. Okay, so it can only have that number. So we cannot create a group of 3 or a group of 6. It has to be in a group of 1, 2, 4, 8, or 16. Okay, now the other rules are we want to make the circles as big as possible. So what that means is we don't want to circle this one and then circle this one when we can make a bigger circle by circling them together. So if we can make a bigger circle, make it bigger. Now I can't make this bigger and circle this group of 4 because then I'd be circling a 0. So we couldn't do that, but we want to make our circle as big as possible. And then the final rule is make as few circles as possible. So we wouldn't want to make extra circles by maybe circling that. This one and this one are already circled, so there's no use in making an extra circle. Now it's okay to circle a 1 more than once, especially if it helps you make a bigger circle. So the reason for this is each circle is going to be one term. If we add an extra circle in, then we're going to add an extra term onto our Boolean expression and make our equation bigger. Also, the bigger we make the circle, the smaller number of inputs we need to put into the AND gate. And so you'll see this when I come up with the Boolean expression. So let's go ahead and figure out what this Boolean expression is. And the idea is that going up and down, A, and this circle right here, A is always 0 and B is always 1. But on C, it's both a 0 and a 1. And the idea is it doesn't really matter if C is a high voltage or a low voltage, it doesn't really matter. As long as A is a low voltage and B is a high voltage, then we should turn our circuit on. So let's go ahead and write that equation out. Okay, so what I've done is I've taken the C that changes, and notice C is both low and high inside of this circle, and I tossed it out. And then I keep the A and B that do not change, a low voltage and a high voltage. I keep them in there, but since A, the first one, is a low voltage, I negate it. And since B is a high voltage, I don't negate it. So now let's focus on this circle and write its equation. And in this case, C is always a low voltage, A is a high voltage in both of them, but B changes as both high and low. So we can toss B out. Now in this case, A is a high voltage and C is a low voltage, so we negate it. And again, B is changing, so we toss it. Finally, in this one, C changes, so it gets tossed. A is a high voltage and B is a low voltage. And because B is a low voltage, it gets negated. And that's it. This is our minimal expression. And as long as we followed all the rules, we're guaranteed to use as few gates as possible. So by circling these guys bigger than just individually, we're able to get down to just 2 input AND gates, which is better than a 3 input AND gate. And also, we only have to have 1 3 input OR gate. Instead, if I made another circle somehow, then I'd have to have a 4 input OR gate. The larger number of inputs in our OR gates, the more transistors those OR gates are going to use. Now here is the resulting circuit that we would create. We would AND A and B together, A being negated for this one. Then we got A and C for this one with C being negated, and A and B for this one with B being negated, and then their outputs feed into this OR gate. Now, before I mentioned that we swap these two rows, so it counts 0, 1, 3, 2. Now don't forget to swap the rows. The reason why we did this is when we swap it, only one bit changes as we go from side to side. Notice from here to here, the B changes. From here to here, the A changes. From here to here, the B changes. If we had these swapped, we'd have both the B and the A changing at the same time, and our K-map would not work anymore. So that's why we always swap these. Now I've drawn up quite a few examples of some K-maps so we can work through this. Now if you want, you can pause the video and then work through it yourself and then come back and see if you got the right answer. Now a couple of notes, I just left all the zeros blank in these K-maps. So if there isn't anything in the square, then that means it's a 0. The other thing, this is a 2 input AND gate with just A and B, and this will still work because we still change just 1 bit moving side to side and only 1 bit moving up and down. Another thing, you already know these are 3 input AND gates, and these two down here are 3 input K-maps, and these two down here are 4 input K-maps with AB going across the top and CD going up and down. So this first letter refers to C, and this second letter refers to D. Now what I also did skip is having a truth table written out and then taking the truth table and putting it into the K-map. All you do is you take the row that corresponds to the A, B, C, and D, take its output, and then put it in the right square. So let's go ahead and walk through making our circles for all of these, and then we'll go ahead and come up with the final Boolean algebra expression. Now on this one, you see that you have a group of 2 here, so you think that you might circle that, but you cannot circle diagonal. It has to go horizontal or vertical. So we have to circle these 2 separately. Now on this K-map right here, we see that we have a group of 4. Now remember, we can circle groups of 1, 2, 4, 8, or 16. So we have this group of 4 right here, so we could go ahead and circle that one. And then we might be tempted to just circle these 2, but remember, we want to make our circles as big as possible, so we can actually circle a group of 4 by doing that. And it's okay to circle these ones more than once, especially when it helps us make a bigger circle. Now, next, we look at this one, and we cannot circle all of these together because then we'd be circling a 0. So we could circle this group of 2 right here, and then we can also circle this group of 2 as well. And then we have this one remaining, so we could circle this one with this one right there. So let's go ahead and draw some circles. And I'm gonna do something different on this one. Now it doesn't matter, we can circle this one with this one, but we can also circle this one with this one. And this is what I haven't taught you about K-maps before, is that you can wrap around the sides. So we can take this guy and we can circle him with that one. So pretend, if you notice, we got 1, 0 here and 0, 0 here. And if we go from this column to this column, we only change 1 bit. So you can circle around like that. Now, it doesn't matter whether you circle it like that or whether you circle it like that. There'll be a different Boolean algebra expression. They'll be equivalent, and they'll also both be minimal. So I'll make that final circle. And when you circle around the side, just have your circle extend a little bit over to show that you're circling around the wrap or around the edges. Now let's go ahead and try to circle this one right here. And I see a nice big group of 4 over here. Okay. Now we can't circle a group of 3 because that's not a power of 2. It's not 1, 2, 4, 8, or 16. So we have to just circle these 2 by themselves. And finally, we could circle these 2 by themselves. Now, one thing that we will not do is make an extra circle. These 2 ones are already circled. There's no reason to make an extra circle. Now, we'll circle this one right here, and I see a nice big group of 4. So that's nice. And then what about these guys? Now I could circle and wrap around like that and make a group of 2. So up and down on these guys right here, we can circle like this. Now you can also circle up and down on that, but that's still the same circle as that. So now we can do a circle like that, but we can also circle around the sides. We can wrap around and we can create a nice group of 4 by circling these 4 corners all together. So watch for that wraparound. I came up with these examples that specifically show you that you can wrap around. So now let's go ahead and write down the Boolean expression for each one of these. So let's look how I created these equations. So they're color-coded, so the color of this circle matches the part of the equation it comes from. And if you notice, A is a low voltage and B is a high voltage. Since A is a low voltage, we negate it. B is a high voltage. Up here, B is a low voltage and A is a high voltage, so we get that. Now we can't toss anything out because these are circles of 1. You won't be able to toss any letters out. So this is our or our minimal equation. Next, we have this big circle here. And if you notice, A changes and B changes as we move across this. So it doesn't really matter what A and B are. As long as C is a low voltage, then we should turn our circuit on. So since C is a 0, notice I negated this C. And now in this circle right here, as we move up and down, C changes. And as we move side to side, our B changes. So as long as A is a high voltage, then we should turn it on as well. Now on this one, we got our circle right here, moving up and down, C changes. A is a high, B is a low voltage. Then this circle right here, if you notice, B is changing. So A is a low voltage, and maybe I'll correct this real quick. So A is a low voltage, and C is also a low voltage, and it's B that changes as we move side to side. And then finally, we have this circle down here that I made. And again, you could have circled this one as well. It would be a different equation, but equivalent. And we could see going side to side, A changes, B is a low voltage, and C is a high voltage. So since B is a low voltage, I negated it, and C is a high voltage. Now let's look at this one right here. And again, the bigger circles we get, it means that when you get a circle of 4, it means you get to toss 2 things out, and C and D change. So it doesn't really matter what they are. As long as A is a high voltage and B is a low voltage, then we should turn it on. In this case, we only get to toss 1 out, and that happens to be our A. So we toss him out. B is a high voltage, and C is a low voltage, so it's negated, and D is a high voltage. And we got this circle right here. B changes, so it gets tossed, but A is a low voltage, so it's negated. Then C is a low voltage, so it's negated. D is a low voltage, so it's negated. So this is the equation for that. And notice we just orient these together. Finally, let's look at this one. Going up and down, you see that C and D change completely. So we can toss C and D for this. And A is a low voltage and B is a low voltage, so they're both negated. So again, it doesn't matter what C and D are, as long as A and B are low, we should turn it on. Now going in the circle in all the corners, if we look, B is a low voltage, so it's negated. A changes, so it gets tossed. And then C up here and down here change. And D is a low voltage, so it's negated. Now, one thing that I'll point out on these K-maps, notice we swap the 2 columns. It goes 0, 1, 3, 2. Also going up and down, we got 0, 1, 3, 2, and we swap that. If you do not swap it, these K-maps will not work because two letters would change as we moved across here and as we moved across there. So hopefully that's a good summary on how you can use K-maps. As you might have seen in the annotations, I didn't do the circling right in this one. Now, it's okay. This Boolean expression will work for this circuit. It's just not minimal because I didn't follow my rules and that I should make my circles as big as possible. Now, I said that you can wrap around from side to side. So what I should have done is made a circle that includes those two and those two. So because I didn't do that, I created one extra circle, and this circle and this circle are not as small as they can be. So what I should do is make a circle that circles those two, and that would make the new equation equal to, now this purple circle is going to stick around, we still need it, and then we could circle all the rest of them in a big group of 4. So let's go ahead and leave the purple circle there, and again, the purple circle, A is low, B is low, where A is low in both, B changes so it gets tossed, and C is low. But now for this new circle that I created that replaces the need for this circle and this circle, in that case, A or C changes on the up and down, so it gets tossed out. A changes too, and we're just left with B being a low voltage, like that. So this equation and this equation are equivalent, but this one is smaller. It only uses one AND gate and one OR gate, which is a lot better than using 3 AND gates and a 3-input OR gate. So again, make sure you don't miss bigger circles that you can possibly make. And so this would be a more minimal equation than this one and a better solution. However, if you built your circuit using this, it would still work correctly, but you'd have a couple extra gates.